Hi guys, this is Terry here. I'm going to go through the solutions to the May 2024 CSEC chemistry exam, the paper 2. So overall the paper was pretty okay, right? Nothing out of the ordinary except maybe for the question pertaining to the water, right? So just some reminders, right? So my new Form 4 chemistry class will be starting in August, and that is for students who are entering Form 4, right, in September, right? Just to give you an idea, in the 2023 exam, which was last year, we had 52 students who got grade 1s in chemistry from my class, right? So they did exceptionally well, all right? Hoping that the results this year are just as good or even better. So let's see. So we have sodium thiosulfate, right? That's Na2S2O3. It reacts with hydrochloric acid to produce sodium chloride, sulfur dioxide, solid sulfur, and water. To investigate the effect of temperature on the rate of reaction, Paul performed different experiments using sodium thiosulfate and hydrochloric acid. For each experiment, the volume and concentration of the sodium thiosulfate and dilute hydrochloric acid were reacted, but at different temperatures, right? So it's a question involving rates, but what we do in here, we are changing the temperature at which the experiment is taking place, right? So they have some experiment 3, 4, 5, 6, 7, and they give us some temperatures. So the first thing, define the term rate of reaction. So this is simply the change, right, in concentration the change in concentration, right, of a product or reactant with time at a stated temperature, right? So we need to put at a stated temperature. Right? So that's one mark here. Should have been 2. Write a balance equation for the reaction between sodium thiosulfate and dilute hydrochloric acid. Right? So we have sodium thiosulfate, which is Na2S2. Right? They give you this in the question. Right? Sodium thiosulfate, you're reacting that with HCl. That's hydrochloric acid. And the products that we're going to get here, they told you in the question. They said sulfur is going to be one of the products. They said SO2. Right? They also said water. Right? So they gave us hints in the question here. Let's go back. So, all right, sodium chloride, sulfur dioxide. So I'm missing sodium chloride, right? So plus NaCl. All right, so let's see if we can balance this equation here, right? Because it's a balance equation, so we need to put, let's put a 2 here by the sodium chloride. So that means we'll have to put a 2 here, right? So let's check. On the left-hand side, we have 2 sodium. Right-hand side, 2 sodium. We're okay. On the left-hand side, we have 2 sulfur. On the right-hand side, we have 2 sulfur as well. Left-hand side, we have 3 oxygen, and we have 2 and 1, 3 on the right-hand side. 2 HCl, 2 H, sorry, on the left. We have 2H on the right, and Cl. Okay, so we get it. That's it. We just need a 2 in front of the HCl and a 2 in front of the NaCl. The next part here, they want us to describe a test and state the observation that can be used to confirm the presence of sulfur dioxide produced from the reaction. So there are several tests we could potentially use here, right? So we can use moist. Right? Now, if you're using litmus, you must say moist. Use moist. Now, SO2 is an acidic gas, right? So moist blue litmus turns red. Right? So moist blue litmus. Right? And observation, it turns red. Right? We have other options here that we could use, right? Other options that we could use, and that includes we can use KMNO4, acidified potassium manganese 7, right? And what's going to happen? It's going to turn colorless, right? So the observation will be turns colorless. Right? In the case of, we can also use potassium dichromate 6. Right? Potassium dichromate, and what happens here, if we bubble SO2 through it, it will turn green. Right? So these are alternative tests we could use. Right? So we have options. What else we want here now? Determine the mass of sulfur dioxide produced when 50 cm cube of gas was collected at STP, right? So let's see. So the first thing I would do, we want how much? The mass. So what I would do, I'd take SO2, right? And I'll work out the molar mass. So sulfur is 32 plus we have 2 oxygen. So that's going to be 2 by 16. So that's going to give you a molar mass of 64. Right, so that's 64 here, and that's 64 gram per mole. Right, that's 64 gram per mole. Now, all we're gonna do, we're gonna say we deal with STP here, right? So so 22,400. So 22,400 cm cube. Right, SO2. Right, is 1 mole. Right, so I'm just doing it in steps here. So 22,400 cm cube at STP is 1 mole of a gas, right? So let's work out for, well, let's change this actually to grams one time. So 22,400 cm cube. So if it's 1 mole of SO2, we just worked out the molar mass of SO2. So therefore that should be equivalent to 64 grams, right? So I'll replace the moles with grams. And therefore, we need to work out for 50 cm cube. That's how much gas is produced. So 50 cm cube SO2, right? And you're going to cross multiply. So that's going to be 50 multiplied by 64, right? All over 22,400, right? And that's going to give me 0.143 grams, right? Because I said, what is the mass of sulfur that is produced when 50 cm cube of gas is collected, right? Let's see what else they want us to work out. So they give us a table here. So we have the different experiments, we have changes in temperature, we have the time taken. So this is a time taken for what? Did they say it was a disappearing cross? Right? I don't even think they said that, right? But we will assume it's disappearing cross because the time represents what? What does the time represent? Right? So let's see. Let's get the temperatures first, right? Right, so that's the third experiment. So from the third experiment, it's 14, right? So the third experiment is 14 degrees Celsius. So this is 14 here. Right? The next temperature, that's experiment 4. That's 20. Right, we need to understand the scale here. So you have 20 here, 21. So that's 20.2468. So that's 20.2, 20.4. That's 20.5. Right, that's the temperature there, 20.5. Right, experiment 5, that's 27, and the next one is 33. So 27, 33. And the last one is 35.24, 35.5. Right, then we want the rate. So to find rate, when you have an experiment like this, rate is simply found by working out 1 over t, right? 1 over your time, right? And you can double check. If you take 1 divided by 59, you'll get 0.017, right? So we're going to take 1 divided by 40, and you're going to get 0.025. Right, next one is 1 divided by 24, and that's 0.042. Right, next one is 1 divided by 15, that is 0.067. Next one is 1 divided by 11, you're going to get 0.091. Oh. And the last one is 1 over 10, which will, well, be 0.1, right? So this is 0 0.0, not 0.0, 0.100, right? So this is my table here for 5 marks. Next part, calculate the 3 decimal places, the rate, right? So they told you how to calculate rate, it's 1 over time, so we did that. So 5 marks for that calculation there. We also got 5 marks for filling out the table, right? The temperature values. So that's 10 marks just for filling out this table, right? The next part, on the axis provided, plot a graph of reaction versus temperature and draw a smooth curve through the points, right? So let me get a copy of this. Alright, so this is the data here that we're trying to plot. Alright, so they've already drawn the axes first, right? They've already drawn the axes first, right? Let's understand the scale. So the temperature axis is fine, that's straightforward. That is, every 2 small line represents 1, so that is fine. On the other axis, okay, that's okay to read off as well. So the first one is 5 against 0.017. So 5 against 0.01. 5, 6, 7, that's here, right? So that's your first point. The next one is, so that's this. Next one is 10 against 0.02. So 10 against 0.02 is here, right? Next one is 14 against 0.025. So 14 against 0.025, that is going to be about, that's here, right? I don't know if you all seen these lines, but they're kind of tiny, right? Next one is 20.5 against 0.042. So 20.5 against 0.042, that's about here, right? So there's a temperature curve. We expect not to get a straight line, right? Next one is 27 against 0.067. 27 against 0.07. All right, so this is 25, 26, right? Kind of hard to read this off here. 0.067, so that is going to be 65, 66, that's about here. All right. The next one is 33 against 0.091. So this is 30, 31, 32, 33 against 0.091, that's up here, right? And then the last one is 35.5 against 35.5 against 0.1, right? This thing is so tiny, I'm having trouble seeing, right? Just now, I feel that point is wrong here because this one says 20.5. All right, is that correct? No, that's fine. Now that looks correct there, right? So that's it. That's my curve. So all you need to do is to draw, take your ruler, your pencil, and you're going to draw a smooth curve through the points, right? That's what we need to do. Draw a smooth curve through the points, right? Right. Hopefully my points are correct. Find the graph looking a little strange. 0.2, 0.02. Next one is 14 against 0.14. Next one is 20.5. Right, I'm just double checking the points here. 27 against 0.067. Next one here is 2t. Right, it seems okay, right? But how much marks are that? 1 or 5 marks a plot, right? 5 marks a plot. Next part. Use a graph, right? You plotted in page 7 to explain how the change in temperature affects the rate, right? So if you notice something here, if we look at the graph, right? Now it isn't a direct relationship because it's a curve. So basically, as the temperature increases, you will notice that the rate of reaction increases. That's as much as we can say, right? So as temperature increases, right? They give us plenty lines here, but it's only 2 marks. So as temperature increases, right, the rate of reaction increases. Right, and that's it for your 25 marks. Relatively straightforward. Right. Next part. Question 2. The most stable form of the element oxygen has mass number 16, atomic number of 8. It can exist as a radioisotope. Define the terms. So atomic number is simply the number of protons right in the nucleus. Right? When you ask you for a mass number is simply the number of protons and neutrons, right? So it's made up of a combination of protons and neutrons in the nucleus. Right, next part, what are isotopes? So isotopes are atoms of the same element right with same number of protons but different number of neutrons, right? Right, so that's question 2. Next part, using a dotted cross diagram, show the bonding present in oxygen gas. So it's oxygen gas, right? So that's O2, right? Oxygen belongs to group 6. So this is what I would do, all right? So this is the symbol for oxygen, right? And I'm going to draw the valence shell here, right? I'm going to draw another oxygen atom close by. So that's your oxygen there, 2 oxygen atoms. And we're going to draw the dot and cross diagram. So remember, each oxygen has 6 valence electrons, right? So 2, right? We're going to put next to here, that's 4, right? Now what's going to happen is that each oxygen atom is going to contribute 2 electrons to form this bond here, right? This covalent bond. So you put a 1 here and you put 1 here, right? So that's your 6 valence electrons on the atom on the left hand side. For the one on the right hand side, right, we're going to use dots to represent that, right? So again, let's put 1, 2, right, 3, 4, right, and we need to put 2 more. So this one is also going to contribute 2 electrons to form that covalent bond. So oxygen is actually like this. There's a double bond between the oxygen atoms, right? So that's your dot and cross diagram there for 3 marks. Next part, they want, there are many uses of radioactive isotopes in everyday life. List any 3 uses of radioisotopes, right? So basically we have, we use them as tracers, right? We use them as tracers, right? And you can give an example, right? We have iodine 131, right? And that is, we use that as a tracer in the body when it comes to the thyroid gland, right? So that's one example, right? We use it as a tracer there, right? 2, we use them in carbon dating, right? So we use them in carbon dating, right? So that's carbon 14. Right? So we also use them, right? We use uranium 235, right? This is a power source in nuclear power plants, right? So this is your raw material we use in nuclear power plants, right? They want 3 of them here, right? What else we could use it for? We use them as a power source for pacemakers as well. So you have more you can use here, right? We use plutonium, right? So we have plutonium, right? And again, as a power source for pacemaker. Right? So in a case like this here, any valid use will work, right? What else we have here now? So that's question 2. That's it. That's all for question 2. Right? The next one here, compound A and B are straight chain hydrocarbons whose molecular formulas are C5H12 and C6H14 respectively. Name or state one natural source of hydrocarbons. Well, petroleum or crude oil, right? It's a very common question that they bring. So petroleum, or we could say crude oil, right? And what is compound B now? Compound B is C6H14, right? C6H14, right? So that's an alkane, right? So this here is 6, so this is called hexane, right? So just to give you context here, right? So this is hexane, it's an alkane, we know that. And we want 2 uses. Now this here, right, because it's C6, chances are it's going to be a liquid. So this here could be used as a degreaser, right? So hexane is used as a degreaser, right? We also use hexane, right, to extract oils from certain seeds, right? So to extract oils from seeds, right? Now basically any example you all give here that makes sense would work, right? But the key thing here, it's a liquid, right? So that means it's a non-polar liquid. So we can use that to clean. So let's say you wanted to clean some car parts that had grease all over it, right? We can use that as a degreaser, right? So any 2 valid example that makes sense will work, right? Draw the fully displayed structure of compound A. Which one is A again? Is C5H12. One second. Okay, so both of them are alkenes, right? So C5H12. Right, so this compound here is C5H12, right? So for 2 marks, we're just going to draw 1, 2, 3, 4, 5, right? And then we're just going to draw some hydrogens. Right, we're getting 2 marks for drawing this. right? So that's 2 marks. Next part now. Draw the fully displayed structure of compound B. All right, so B is, so they're giving away marks here, guys, right? This is very simple stuff here. C6H14. So C6H14, right? So we're gonna draw 1, 2. Now they told us a straight chain, that's in any question, so no need to draw any rings here, right? So that's 1, 2, 3, 4, 5, 6. Right, so that's part 2. List any 4 general characteristics of a homologous series. So this is a question they repeat so many times, right? So same general formula. Right, 2, same functional group. Right, similar chemical properties. Four physical properties vary with the number of carbon atoms, right? Right, and we could put a 5th one here if you want, right? Adjacent members differ by CH2, right? Adjacent members. Right? Now they said deduce the homologous series to which compound A and belong, right? A and B. So we already established that's an alkane, right? See what else we have now. Compound D is C6H14, right? It burns completely in oxygen to produce CO2 and water. All right, so C6H14, right, burns completely in oxygen. So you're gonna add O2. And the 2 products here, it's an alkene, so we should only get 2 products, which will be CO2, right? They don't want state symbols. Oh yes, they do, right? So state symbols here, so we need to put liquid, we need to put gas, right? Or carbon dioxide gas as well, right? So usually when you see 3 marks here, chances are they want state symbols. So they want state symbols, right? Plus H2O liquid. So you get a mark for putting in the state symbols, by the way. So how do we balance this? So what I normally tell my students in class, the first thing we do, we balance the carbons, right? That's step 1. So in this case here, we have 6 carbons on the left. So we're gonna put 6 carbons here. Next thing, I've told them to balance the hydrogen. So you have 14 on the left. So to make this balance, you need to put a 7 here, right? So now when you look at the next last thing to balance is the number of oxygen atoms. So on the right hand side, you have 6 2s are 12 plus 7, so that's 19. So therefore, this here will be 19 over 2, right? So this is typically how I teach my class to do it, right? But we don't leave our answer like that. What we do, I tell my students to multiply everything by 2 here to get rid of the fractions. So it's going to be 2 C6H14 liquid, right, plus 19 O2 gas, right, produces, this will be 12 CO2 gas, right, plus 14 H2O liquid, right? So this here would be the answer here, this one, right? So that takes care of your third question. Fourth question here, right? Magnesium and lead are metals often found in living things and in the environment. Explain metallic bonding in metals, right? So this is typical question again, metallic bonding, right? So positive metal ions, or you can say cations, right, held together by a sea of mobile electrons. Right? So that's what metallic bonding is basically, right? So if you had to, let's say they had access to draw a diagram, right? Within the metal itself, we have these positive ions, right, which we call cations, right? So these are throughout the structure, right? And then inside the structure, you have these electrons, which are also mobile, right? So that attraction between the electrons and the cations, that is what we call metallic bonding, right? So they said give a reason why metals conduct electricity in a solid form. You need to say that the electrons are mobile, right? You can even use the word delocalized if you want, meaning that they're not fixed to any one cation, right? Next thing, state any two harmful effects of lead and its compounds on living things and the environment, right? So we know that lead is very poisonous, right? In the case of children, right? So children, right? If children were to get lead into their system, right? What can happen is that you can have brain damage, right? You can have brain damage, neurological disorders, right? You can have coma, you can have death, right? All of this could be caused from lead poisoning in kids, right? In adults, right? If you ingest it, right, we can have stomach issues, right? Or intestinal issues. Right? Things like colic, right? So the thing is, lead affects our central nervous system, right? That's what it does. It affects our central nervous system. So even in adults, you can get some fingers could become paralyzed because of lead in our bodies, right? So any two harmful effects here, right? So this question can go either way here, right? Next part. We have a chemistry student conducted a series of experiments using the electrolytic cell to test the conductivity of magnesium chloride. The materials used to set up the apparatus and the students' observations were recorded in table 2. So we have 3 different experiments here. So in one experiment, we're using PVC plastic as the electrode. Then we have graphite, we have platinum. And we have scenarios where the bulb will either light or not light. And observations at the electrodes. No visible change, no visible change. All right, let's see what they want here, right? So this question here is with 4 marks and there are lots of lines, so we have to explain certain things, right? Explain why the bulb did not light in experiments 1 and experiment 3. So let's look at experiment 1 here. So in experiment 1, right, what do we have? We have PVC plastic, right? We have PVC plastic. We have dilute aqueous magnesium chloride. And the bulb doesn't light, but that makes sense, right? Because in order for you to get the bulb to light, we need a complete circuit. PVC plastic is not a conductor of electricity, right? So explain. So you're going to say PVC, right, is not an electrical conductor, right? So we need to say something along those lines, not an electrical conductor. Right? It's not an electrical conductor, and therefore That's, yeah, and therefore. Right, there is no complete path. Right, I want to say path, I mean PATH. Path to form a circuit for the bulb to light. So those of you doing physics will know that's an open circuit here, right? All right, so that's experiment 1. Third experiment, the bulb doesn't light either. So we have platinum. Well, platinum is a conductor, yes, but what we notice is that we have solid magnesium chloride. So therefore, magnesium chloride, MgCl2, right, is an ionic compound. Right, in the solid state. The Mg2 plus and the Cl minus are fixed in the ionic lattice. Right, so they're fixed in the ionic lattice, so they can't move. Right, so the ions are not mobile. So that's why it wouldn't light. The ions are not mobile. Right, so that's part 1. Explain why the bulb lit in experiment 2. So let's go back to experiment 2 here now. What's happening in experiment 2? Right, so we have graphite. Graphite is a conductor. Dilute aqueous magnesium chloride is a conductor as well, right? And the bulb lights. So what is going to happen here? We need to say that graphite is a conductor. Right, because it has mobile electrons. They give you plenty lines here, so you should try to say as much as you can, right? So graphite is a conductor because it has mobile electrons, right? Next one here is the magnesium chloride solution, so that's MgCl2 aqueous, right, is a conductor. Because the ions, so you need to be specific in your words here, because the ions are mobile in solution. Right? So basically what you have here, you have a power supply, right? You have your graphite electrodes here, right? And you have a bulb in the circuit, right? And the bulb is lighted, right? The bulb is going to light here. So what's happening here is that you have this solution of magnesium chloride, which is MgCl2 aqueous, right? So therefore you expect the bulb to light, right? You have your ions in your solution and you have graphite as a conductor, so there's a complete loop for current to flow and the bulb lights, right? So you can see that there is a complete loop. And the bulb lights. Right? Next part, state the process that took place in experiment 2. So this is experiment 2 here, right? So the process that's going to take place here is going to be electrolysis. Right? Because I think, let me see the table. So in the table, look, they said something happened. Gases are produced at the cathode and the anode, right? What else we have here? Magnesium readily reacts with oxygen in air. Write a balanced chemical equation for this reaction. So magnesium, now they didn't ask for state symbols, but I'm still going to put it, right? If you didn't put it, that's okay. So magnesium plus oxygen, right? Gas. We're going to get an oxide. In this case here, we're going to get MgO, right? Solid, right? This is not balanced, so we need to put a 2 here and we need to put a 2 here, right? And that's it. That takes care of question 4. Right, this is question 5. Define the term, proteins and starch are examples of natural polymers which are formed through the process of condensation polymerization. Define the term polymer, right? So standard question that they bring a lot, right? So a macromolecule made up of many repeating units called monomers. Right? Next one, define condensation polymerization. Right? So polymerization where monomers, right, or maybe one or two monomers, right? They're only giving us 1 mark for this, right? So polymerization where 1 or 2 monomers combine to form a polymer, right, with the release of small molecules right? Example, water, right? So that's a condensation polymerization process we're talking about here. So 2 or more monomers, they combine, and in the process, we have small molecules being released, right? So that's part A. All right, one sec. All right, so part B, part 1, define the term fermentation. So basically, with fermentation, right? So it's the breakdown of sugars, right, with yeast, right? So we can say breakdown of sugars with yeast by anaerobic right? So anaerobic means without oxygen. Right, so breakdown of sugars with yeast by anaerobic respiration, right, to produce ethanol, right? So that's essentially what fermentation is. All right. Now, write a balanced chemical equation including state symbols to show the process of fermentation. So we start off with a sugar, C6H12O6. Right? Now, this here is going to be aqueous because it's in solution, right? And what's going to happen here, so we have yeast, right? In yeast, we have an enzyme called zymase, right? So what we're going to get here, we're going to get our ethanol, which is C2H5OH aqueous, right? Plus, we're going to get carbon dioxide gas, right? CO2 gas, right? You're getting marks with state symbols. That's why you're getting 3 marks for this, right? The equation is not balanced. So if we put 2 here, and let me put a 2 here and see what happens. So 6 carbon on the left, we have 2 2s are 4 and 2 6 on the right. We have 12 hydrogen on the left. We have 5 2s are 10 and 2 12. Okay. 6 oxygen on the left. We have 2 and 2 2s are 4. We have 6. So this is my balanced chemical equation for the fermentation process, right? The next part here, draw a fully displayed structure of ethanol. So ethanol is 2 carbons. Right, so that's ethanol there, right? Easy 2 marks. Next part here, during a demonstration of the winemaking process in the school's food lab, a technician separated a pure sample of ethanol. However, the flask was not labeled and water was accidentally poured into the sample. Using a line diagram, right, draw and label the apparatus that could be set up in the lab to obtain pure ethanol from the contaminated sample, right? So basically what we need to do here is fractional distillation, right? And that's because water has a boiling point of 100 degrees Celsius, right? And your ethanol boils at about 78 degrees Celsius, right? So to draw the simple line diagram here, I'm not going to draw it, right? I'm just going to give you what it is, right? So this is my diagram for my my class, right? So basically, this is the diagram that we need to draw for our answer here, right? But in this case, it's not the fermentation mixture we have here, right? This is not the fermentation mixture. That's a mixture of water and the ethanol, right? So you need to label it. So this here is what we call the condenser. So this is the condenser. Right? So you also need to make sure that the water enters from the bottom of the condenser and leaves from the top. We need to ensure that we label the thermometer, and the thermometer, if you notice, it lines up right here where the vapor is going to enter the condenser, right? So what's going to happen if you have a mixture of water and ethanol? Ethanol is going to boil up first because it has a boiling point of 78. So we're going to collect the pure ethanol on this side here. So a simple diagram like this will suffice for the exam, right? And the last question here, Alka-Seltzer and Epsom salts are common remedies in the Caribbean, right? Alka-Seltzer is an antacid to treat upset stomach, and Epsom salt is used to treat sprains and muscle pain. The active ingredient in Alka-Seltzer is sodium hydrogen carbonate, and in Epsom salt it is magnesium sulfate. So if you never heard these words, they're kind of telling you what is found in it, right? Now, water is called the universal solvent because it dissolves many substances. Epsom salt and Alka-Seltzer work by dissolving in water. Explain why water is a good solvent, right? So basically, water, right? So the formula for water is H2O, right? So basically, the water molecule, right, right, is polar, right? And the reason why it's polar is because, now it's 2 marks here and they give us plenty lines, so you might as well write what you know, right? So oxygen is more electronegative than hydrogen. right? Making the OH bond polar. Right, and we could also say that this makes it a good solvent, right, for ionic compounds. Right, so anything along these lines here. There's only 2 marks, so trying to put as much as you can in the answer. State 2 properties of water other than it's a good solvent, right? So they want properties of water, right? So they only want 2, so any one you remember will be fine. So you could say high specific heat capacity, right? You can also say high boiling point, right? 100 is a high boiling point, eh? Right, which is 100 degrees Celsius, right? High surface tension. There are some insects that actually walk on water, so high surface tension. Right. So any 2 properties you could come up with, that's fine, right? They said state any 2 other compounds that dissolve in water. So any 2, you all could say anything you want here basically, right? So sodium chloride, that's in your kitchen, right? Common salt, that would be my answer here for this one for sure, right? Sodium chloride, right? They don't want the formula, they just want the state any 2, right? Sodium chloride, but the formula is NaCl, right? And based on what we know about solubility, right, all nitrates are soluble, right? So we can say something like potassium nitrate if we want, right? I'm going to write the formula, but so basically just give them 2 soluble salts and you're okay there, right? Potassium nitrate, right, which is KNO3. So any 2 that you give, you should be able to get a mark. Next one here. Continuous use of Epsom salts. Now at the beginning it told us that Epsom salt has magnesium sulfate in it, right? So Epsom salt has magnesium sulfate, right? So continuous, right? So magnesium sulfate, right? Continuous use of Epsom salt in water may cause hardness of water. This does not happen with Alka-Seltzer. State the type of water hardness. So we have 2 kinds of hardness. We have soft water and we have hard water, right? But when it comes to hardness, we have temporary hardness and we have permanent hardness. When it comes to magnesium sulfate, that causes permanent hardness, right? Permanent. Right? So that's what we're looking for here. Now, explain why Epsom salt causes hardness of water, right? So all we need to say here, I'm going to give us plenty of lines here, right? The Mg2 plus, right, in the magnesium sulfate, right, causes the permanent hardness. Right. Now the thing is, this permanent hardness here, we can't boil the water to remove the hardness, right? You can't boil the water to remove it, right? That can only happen with temporary hardness. I'm just trying to figure out what else they want here for 2 marks. I find out this is not too much here for, not enough for 2 marks. The Mg2 plus in the magnesium sulfate causes permanent hardness, right? So here's what I would include. I'll try to put more right, than is probably required. So the hard water, right, does not lather easily with soap, right, and forms an insoluble scum, right? And that scum is being formed because of the magnesium ions that are present, right? Let's see what else we have here. Explain why boiling water will not remove the hardness in Epsom salt, right? So remember we have MgSO4, right? Why will boiling? So the reason why boiling removes temporary hardness is because temporary hardness is caused by hydrogen carbonates. When you warm a hydrogen carbonate, it decomposes. So all you're going to say here is that MgSO4 is stable, right? Stable and does not break down when heated, right? Third part. What else we have here now? Identify two salts that cause hardness of water that can be removed by boiling. So Ca2 plus, right? That's all. Yeah, Ca2 plus, right? And Mg2 plus are what are the ions responsible for the hardness of water, right? Ca2 plus and Mg2 plus. But when it comes to they want us to remove it by boiling, right? That's the hydrogen carbonate. So the two salts that we could put here is CaHCO3 taken twice. That's calcium hydrogen carbonate. And we can also have magnesium hydrogen carbonate, right? So these are the two, right? These are the two salts that can cause hardness in water, and we can remove them by boiling, right? So that's the answer I would give there. The next part, when used as an antacid, Alka-Seltzer neutralizes HCl in the stomach. So in the question, I think they told us what was an Alka-Seltzer. That should have been sodium hydrogen carbonate, I believe it was. Yes, they told you we have sodium bicarbonate or sodium hydrogen carbonate. So therefore, we're going to take sodium hydrogen carbonate. Now they didn't ask for state symbols, so I'm not going to put any, right? Plus HCl. So this is the reaction we're going to get. You're going to get a salt. In this case, we're going to get NaCl. Plus, we should get some water coming out here. All right, and we should also get carbon dioxide coming out here, right? In terms of balancing equation, we have one sodium on the left, one sodium on the right. You have two hydrogen on the left, two on the right, three oxygen on the left, three oxygen on the right, one chlorine. So we're looking good there, right? There's no, we don't have to include anything else, right? And guys, that's it. That brings us to the end of the 2024 solutions for the Chem Paper 2, right? So guys, please remember to hit like and subscribe, right? And my new classes, right? My new classes will begin in August, right? And my classes usually takes a year and 8 months to come. Well, in terms of preparing for the exam, right? So that new class will be preparing to write in 2026, all right? All right, guys, take care.